Hi, Olkar here. Today it's time to tackle the most important and unique part of the game, which is combat. But before we dive into that, let's quickly go over what's changed since the last devlog. First, I updated the main character model using the new asset pack I bought. The pack is great, and unless the game attracts overwhelming attention, I will probably stick with this visual style. The low poly look also helps the attack effects stand out more clearly, and that's important since those effects play a big role in the gameplay, so that's another bonus. I also bought a pack with water effects, and they look fantastic. They fit really well with the overall art style, but we'll take a closer look at those a bit later. Like I mentioned in the concept devlog, the core mechanic of the game is going to be the attack system. In order to perform an attack, the player will need to make circular motion with the analog stick or mouse. This simulates winding up the weapon. And the faster the player spins the mouse, the faster the attack will charge, but also the higher the speed they will need to maintain in order to keep that power level up. It might sound a bit confusing now, but it will make all sense once I show you the prototype for the throw mechanic. In the game, there will be one type of attack, but it splits into three distinct phases. First one is preparation, next one is melee attack, and the last one is throw. Now that we have covered the theory, let's take a look at the prototype I mentioned earlier. Alright, as you can see, I have prepared the prototype for the throwing mechanic. One thing I didn't mention earlier is that with this approach we lose the ability to aim freely while charging the weapon. To make up for that, I added a directional spread. The range of possible throw angles increases with the throw's power, so the more power you build up, the wider the aiming range becomes, which still allows for some level of precision. This mechanic will also interact differently depending on how long the round has been going, thanks to a system I'm calling ascendancy. But we'll talk more about that later. To summarize, the throw mechanics consist of the following steps. First, you aim, then you start spinning, which locks your aim in place. Next, you build up spin to your desired power level. Finally, you release the spin button, which triggers the throw. Also, quick apology for any typos. I know they can be painful to look at. Now let's go through the code. The entire throw mechanic is handled by a single script, but each part of the process is split into separate components. This makes the main throw controller very simple in structure. Each stage of the throw is managed by its own dedicated module. The controller itself only decides when each part should happen. Another thing worth mentioning, the game is already set up to support multiple input types. Since different controllers measure spin speed in different ways, I use the strategy pattern to handle that out. This means adding support for a new input device is as easy as writing a new case and plugging in a new calculation method. Alright, now that the mechanic is in place, it's time to add some animations, because let's be honest, we are not getting far without those. So let's jump into the animation software and I'll see you in a second. Okay, so after adding the animation, here's what the attack looks like. It's looking pretty good so far, but there's still no weapon, and that's kind of important. So next up, let's implement the weapon for our warrior. For now, I'll use a placeholder model for the asset pack, but later we'll replace it with something that fits better, something worthy of a weapon sent by the gods. Let's go over what still needs to be added for the attack to be fully implemented. Since the throw mechanic is already working on a technical level, we can now focus on the two remaining parts, the preparation phase and the melee attack phase. To do that, we'll use our character's state machine and add a new state especially for throwing. As you can see, when the throw starts, the code triggers the throw animation and begins the throw sequence. This tells the weapon that it's time to begin the throwing process. Now, here's where things get interesting. Once the player enters the throw state, I design it so that the weapon itself decides what state it should be in. That's why I also added a separate state machine to the weapon. Just like the character, the weapon is split into individual states that control how it behaves at each step of the process. Before I show you the final result, let's quickly go back to the water effects. As I mentioned in the concept video, are sent down by the gods, and each god grants a weapon infused with elemental energy. Right now I only have the water effects implemented, but we'll be adding the other elements later on. There's also one more visual effect I added. It signals to other players that we are about to throw. I actually made this one myself, and honestly, I'm really happy with how it turned out. So here's how the attack looks after adding all the effects. Now you're probably thinking, okay, but where's that motion-based throw you mentioned at the beginning? And you're obviously right, so let's get into that now. Right before the throw, the player needs to spin the weapon using circular motion on the controller. The faster you spin, the more power you build up for the throw. This whole motion is going to be represented with special visual effect, kind of like power up, build up. That's scaled dynamically with the speed of your spinning. Similar to the flames above the score in Balatro. Alright, it's back to animating. This time we need to create the spinning animation. Okay, here's what it looks like so far. Let's just say it's not bad for now. Next, we need to make the animation speed dynamic. To do that, we'll take advantage of Unity's features and add a speed multiplier to the animation, which we'll control through code. Let's test it out and see how it works. Alright, the spinning speed effect looks great. Now let's move on the weapon itself. We'll need to do a bit of math here to calculate the weapon's position along a circle. Basically, this represents the length of the rope it's attached to. To make the visuals more interesting, the weapon won't spin flat. Instead, it follows the edge of a cone, giving it a bit more dynamic motion. And as you probably noticed during the throw animation, we also need an actual rope connecting the weapon to the character. But let's take it one step at a time. Let's take care of the position on the circle first. To calculate where the weapon should be along the circle, we will use the simple formula. If we know the angle we want to rotate the kunai by, we can figure out its position using the Pythagorean theorem and some basic trigonometric properties. Alright, now that the kunai properly follows the player, it's time to solve the next problem. It needs to be attached to something. So let's move to the topic that took me way too long, and you will see why. Researching how to simulate a rope actually took us all the way to the orbiting rockets. So yeah, things get serious. Long story short, the rope is basically a set of points affected by physics forces. Okay, not quite a rope yet, so let's add some constraints. To create a rope, we need to establish constraints between each point, which in this case mean to establish maximum distance between points. And there's where things get tricky. Computers don't work in true real time, they only simulate it. In other words, there's no smooth continuity, just a series of discrete moments, as close together as possible. You can understand this better if you think about FPS in-game. Frames per second are basically how many time points we calculate every second. It's a simplification, but it helps make the concepts clearer. Because of those gaps between frames, we have to guess what happens in between. And that's the problem. Take a look at this image. This is called slope field. It's basically a field of tiny lines that shows the direction and angle a curve would follow if it passes through that point. That curve could represent something like velocity, derivative of position. Now, as some of you may have already noticed, everything works fine if we have continuity. But without it, we have to assume the slope, some rate of change, and that introduces error. This is where numerical methods come in. And yes, this is the part where I mentioned the orbiting rockets. Though some numerical methods were used to brief spacecraft safely back to Earth. We will use them here to predict where our row points should be between frames. Specifically, we are using something called Verlet integration, which has a nice side effect. It naturally dumps energy over time, which helps us keep the rope stable and smooth. After a little help from this guy right here, and after implementing everything we talked about, it's finally time to show the rope in action. Okay, if you squint hard enough, it kinda look like a rope. And that's because ropes tend to stretch. Time-stepped physics can't perfectly preserve the distance between mass points. Numerical errors accumulate over time, and as a result, the segments slowly become longer than they should be. Even with Verlet integration, these errors are still there, and the rope gradually stretches. To fix this, we'll use something called the Jacobsen method. Jacobsen method, also known as constraint relaxation or position-based dynamics, fixes the problem by correcting points' positions after each physics step, forcing them to stay at the correct distance. That keeps the rope from stretching and makes it behave much more realistically. Alright, with everything we've implemented so far, it's time for the final test. Let's see how the rope behaves now. Now it's actually look like a rope. I would say that's a win. Next up, let's finally attach the rope to our weapon. And done! The weapon's ready, and the rope is looking really solid. That's it for today's devlog. In the next episode we will work on the core attack functionality, introduce the ascendancy mechanic, and add some special effects to make the attacks more visually exciting. Let me know in the comments, do you like how the rope turned out, or maybe you know a better way to implement it. Thanks for watching and see you next time.